Hi, welcome to this lecture on data abstraction. This is the second part of our two-part introduction to Java. In this lecture, we are going to focus on Java programs as data type definitions. We'll first talk about how you use abstract data types, or ADTs for short, and then we will discuss examples of abstract data types, and then we'll talk about how you implement an ADT or an abstract data type, and finally we'll talk about some data type design principles. So an abstract data type, or ADT for short, is one whose representation is hidden from the client. All right, and we use an API to specify the behavior of an ADT. So the client is aware of the ADT or the abstract data type only through the API, and the client is completely hidden from the representation of the abstract data type. So the internal representation is not available to the client. Here is an example of an ADT. It is a data type called Counter that models a counter, something that you can use to count operations. And this data type is comparable in that you can compare two objects of the counter data type for order, meaning you can tell which one is smaller, for example. All right. So let's go through the API. So the first method that you see in the API called Counter, that has a special status. It's called the constructor. Okay, and that's what allows you to build an object of the counter data type. So we can build an object of counter, giving the constructor the ID of the counter as a string. And once you have an object built of the counter data type, you can increment its count by making a call to the increment method, which simply increments the counter by 1. And then you can use the tally method to check the current count that the counter maintains, which is basically the number of increments that were done since creation. And then you can get hold of a string representation of the counter object by making a call to the toString method. And finally, you can use the compare2 method to compare two counter objects and figure out which one is smaller. And the way compare2 works is that it returns an integer depending on how the two counter objects compare. The one that on which you're calling the compare2 method, and the other one that is passed as an argument. And this method basically returns 0 when the two counter objects maintain the same count. It returns a positive number when one of the counters is larger than this one, and it returns a negative number when one of the counters is less than the other counter. We'll talk about how you make a type comparable later on in this lecture. Okay, so now let's talk about the similarities of an abstract data type with a library of static methods that we discussed in the last lecture. Now, both a library of static methods and an abstract data type are implemented as a Java class. Now, instance methods, such as the ones that you saw in the API for Counter on the previous slide, they are similar to static methods in that they may take 0 or more arguments of a specified type, separated by commas and enclosed in parentheses. Instance methods also provide a return value of a specified type or no return value, which is signified by the void keyword. So instance methods or abstract data types are quite similar to a library of static methods. what are the differences then? So how is an ADT different from a library of static methods? Well, some entries in the API called constructors are special, and they have the same name as the class and they lack a return type. So that's how you tell a constructor apart. So when you look at the API for an ADT, if you see a method that has the same name as the class and does not have a return type, not even void, then you can tell that it is a constructor. Now, library of static methods does not have a constructor. Okay, so in that sense, ADTs are different from a library of static methods. And then instance methods, which are the methods that belong to an abstract data type, they lack the static modifier. Okay, so here's another big difference. And the purpose of the instance methods is to operate on data type values or attributes of the data type. And then some instance methods are inherited from parent class. So it turns out that you can have one ADT inherit from another, and some of the instance methods are inherited from the parent ADT. Okay, so these are some of the differences of an ADT from a library of static methods. Okay, so the two, ADTs and a library of static methods are similar in many ways, but they also have some significant differences. Now, every Java data type, every type that you implement, inherits from a data type called object that sits inside of the java.lang package. Okay, so there is a class hierarchy in Java, and at the root of this hierarchy you have the object class. And every data type that you implement, such as counter, for example, inherits from this object data type. Okay. Now, this data type object has some methods in it, such as toString, that returns the string representation of the object, equals method that can be used to compare one object with another, and the hash code method, which returns a unique identifier for an object. So these are all methods that are defined in object. And since counter, for example, inherits from object, counter also inherits these methods from object. Okay. Now you can choose to re-implement these methods inside of your data type the way you want, which is what you typically do. For example, if you want the string representation of an object of a type that you are implementing, you would implement the toString method. In other words, you would override the toString method, and then if you want to compare two objects of your data type, then you would override the equals method from the object data type. All right. And if you don't do that in your data type, then you get the default implementations that are available for these methods within the object data type. And the default implementation is to simply work with the memory address of the objects. Okay? And that's typically not what you want. So you usually end up overriding these methods inside of your data type. And the same is also true with hash code. Hash code at the level of an object simply returns the memory address of the object as a unique identifier of the object. But if you want to give it a different meaning, then you will have to override the hash code method inside of your data type. Okay? All right, so every Java data type inherits from object. Or in other words, object is at the root of the class hierarchy in Java. Now, an object is an entity that can take on a data type, a value. Okay, and this will become clear later on. And an object of a data type is characterized by three things. its state, meaning the values from its data type, its identity, meaning the place of the object in memory, and also its behavior, which is characterized by the effect of the data type operations. All right. So again, an object is characterized by three things. Its state, meaning the values from its data type, its identity, meaning where it's located in memory, and its behavior, which is given by the data type operations. Now, how do you create an object of a data type in Java? Well, to create an object or to instantiate an object, what we do is we invoke the constructor. Okay? And we do so using the keyword new. And the keyword new is followed by the name of the class, the name of the abstract data type, that is, followed by 0 or more arguments for the constructor, enclosed in parentheses and separated by commas. Now, going back to our counter data type from before, let's say we want to create a couple of objects of this data type. Let's say we want to create a heads counter and also a tails counter. And the reason we want to do this is because let's say we are performing an experiment where we are flipping a fair coin many times, and we want to figure out the number of heads that appeared and the number of tails that appeared. So we're going to use the heads counter to count up the number of heads, and we're going to use the tails counter to count up the number of tails. So how do you create these objects? Well, that's what is shown here. So we put the name of the type. So remember that in Java everything has to be declared. So we are saying that we have a variable called heads that's of type counter. So that's the declaration part, and on the right hand side we have the initialization. So we're saying that heads is a counter object, and we do that by using the keyword new, followed by a call to the constructor of counter. So we call the constructor, giving it the string ID, and here we use the ID heads. Right? So that's what creates an object called heads of type counter. And then we do the same thing for tails. We say tails is an object of type counter, and on the right hand side we have the initialization that says new counter, which is the call to the constructor, with the string ID set to tails. Right? So once these two statements are executed, we have two objects in memory. We have the heads object and the tails, and both heads and tails are of type counter. Now let's talk a little bit about object representation in memory. So whenever you do something like this, when you create an object, what can you tell about the variables heads and tails? Well, the name of the object or these variables heads and tails, what they store are memory addresses. They store the memory address of the corresponding object. So for example, heads might just store the number 460, which is basically a memory address, and tails might store 612, which again is simply a memory address. Now, if you go to those locations in memory, so for example, if you go to 460, that's in memory, what are you going to find there? Well, that's where you will find the identity of the heads object. Okay, remember what we said before. An object is characterized by three things: its state, its identity, meaning its location in memory, and the behavior given by the data type operations. So if you go to the memory location that is given by the name of the object, at that location you're going to find the identity of that object. So if you go to 460, you'll find the identity of heads, and if you go to 612, you'll find the identity of the tails object. Okay, so that's how an object is represented in memory. Now, what is the purpose of an instance method? Well, the purpose of an instance method is to operate on data type values or the attribute values. So each data type has a collection of attributes, and an object of that data type has values for those attributes. So the instance method typically operates on those attribute values or data type values. Now, how do we call an instance method? Well, an instance method is invoked as the object name followed by a period followed by the name of the instance method followed by 0 or more arguments enclosed in parentheses and separated by commas. Okay, and notice the difference between how you invoke an instance method and how you invoke a static method. A static method is invoked by saying the type name dot the method name followed by the arguments, whereas here with an instance method, the way you invoke it is by saying the object name dot the instance method name followed by arguments. Okay, so the thing that goes before the dot in the case of an instance method is an object of a data type, whereas the thing that goes before a dot in the case of a static method is the type name itself. So for example, math.square root. Okay, so square root is a static method and it is invoked on the type math. So that's an example of a static method call, and whereas an instance method is invoked on an object. Okay, and we'll see examples of this very soon. So let's look at an example where we want to write a program called flips that simulates T coin flips, capital T coin flips. All right, meaning we want to flip a fair coin capital T number of times, and we want to keep track of the number of heads and the number of tails. So here is a program that does that. It's called flips. We first import some libraries. So we import the counter data type from this package, and then we also import the libraries stdout and stdrandom. Now counter is an ADT, and stdout and stdrandom are library of static methods. Okay. All right, and this program is going to make use of the counter data type to just keep track of the number of heads and number of tails. Okay, so let's go through the program. The class or the program is called flips. It's public and it's a class, and then it has a single method, the special entry point method called main, public static void main. Okay, so when you run this program, it's the main method that is invoked, and this array we know stores the command line arguments. Okay, so what are we doing? The first thing that we do is get the first command line argument argz0 as an integer and store it in the variable capital T. And that's going to denote the number of coin flips that we want to perform. So we receive that as a command line input. Okay, and if you recall, parseInt is a static method in integer that converts a string argument into a primitive integer. Okay, so that's that. And then what we do is we create two objects of type counter. The first one is called heads and the other one is called tails, and this is what we had in the previous slide. And the way we create an object of type counter is by saying counter, the name of the variable, heads in this case, equals new, called to the constructor with a string ID. Okay, and then the same thing for tails. So we have two counter objects, heads and tails, and then what we do is we simulate the capital T coin flips. So little t goes from 0 all the way up to capital T in increments of 1, and what we do in the body of the for statement is quite simple. We make use of the static method Bernoulli from stdrandom, giving it an argument of 0.5 because we are simulating a fair coin, and if this is true, then we think of it as heads. So what do we do in that case? Well, we increment the heads object by 1. Otherwise, meaning if this turned out to be false, we look at it as tails, and in that case we increment the tails object by 1. Okay, now this is where we see calls to instance methods. All right, so increment, if you remember the API for counter, increment is an instance method belonging to the counter data type. Since it's an instance method, you call it on an object, and in this case this is an object of the counter data type. Okay, and what effect does this have? Well, it has the effect of incrementing the heads count by 1. Similarly, here increment is an instance method, and since it's an instance method, it must be called on an object, and this is indeed an object. It is an object of type counter. And what effect does increment have? Well, it has the effect of affecting the data type value for tails, and meaning it increments the tails counter by 1. All right. Okay, notice that it's the same increment method, but it's operating on different objects. So here it operates on the heads object, and here it operates on the tails object. Okay. Now, once the for loop is done, meaning once we have performed capital D number of iterations, then the heads and the tails object, they have the appropriate tally, and what we do next is we simply print the two objects. Okay, so we print the heads object and we also print the tails object. Now here there is something that is going on behind the scenes that you should be aware of. So whenever you print an object, okay, such as heads for example, then this is absolutely equivalent to saying stdout dot println of heads dot toString. Okay, so internally the toString method of the heads object is invoked, and whatever is returned by that method is what gets printed. All right, and if you remember what we said before, toString is a method that's defined in object, and counter is a data type, is an abstract data type that inherits from object, and toString that's available here simply returns the memory address of this object. But as we'll see later on, counter actually overrides this toString method to provide something meaningful about a counter object. Because when you print a counter object, we don't really want the memory address of the object. We would rather have the tally that that object maintains. And that's exactly what the toString method in counter does. And we'll see this later. Okay. So whenever you print a counter object, what's going on is behind the scenes, it's the toString method of that object that is being invoked, and whatever that returns is what gets printed out by println. Okay, and the same is also true about this statement here. So here the toString method on tails is invoked, and whatever that ends up returning is what gets printed. All right, so so that's what happens when you try to print an object in Java. Okay, and then what we do is we calculate the difference in tally between the heads and tails, and here we make a call to another instance method from the Counter ADT. So we make a call to the tally instance method on the heads object and subtract from that what is returned by tally called on tails. So delta is simply the difference in counts. Okay, the number of heads minus the number of tails. And finally, what we do is we simply print the absolute value of that difference. Okay. So this is a string, and we concatenate to that the absolute value of delta. Now this is not a string, but from our discussion before, from the previous lecture, we know that this guy here gets promoted to a string. Okay, and then that string gets concatenated to this one, and that's what ends up being printed. Okay, now before proceeding further, let me just point out a few things. So tally is an instance method called on an object. So here again, tally is an instance method called on an object of type counter. There are also some static methods calls in this program. So what are those? Let's identify those so we have a good handle on instance methods and static methods. So this guy here is a static method. I'm going to put that in a box. Static method called on the type integer. Okay. What is another static method? Well, this guy here is a static method, ABS, called on the library math. Okay. What are some of the other static methods? Well, println is a static method. And notice how it's called. It's called on a type. Okay, stdout is a type. It's not an object. So, and here's another example of a static method. Bernoulli is a static method. Okay, and what's the type? It's std_random. So I hope this gives you an idea on how instance methods work and how they are different from static methods. Okay, so let's now look at some output of this program. So remember, you first compile this program. I have suppressed that line here. So you say java c flips.java, and that produces flips.class, and you simply run flips. Now flips expects a command line argument, capital T. So in this case, you supply that as 1,000,000. And what the program comes back with are the counts, the number of heads and the number of tails, and also the delta. Okay, and this is a random process. So if you run the program again, you will see different counts, right? But it'll be sort of in this ballpark, roughly 50% heads and 50% tails. Okay, now before moving on, let me just point out one thing, that this output here is basically what you get by printing the heads object. Okay, and this output here is what you get by printing the tails object. So that should give you some idea on what the toString method of the counter data type returns for an object of type counter. Okay, all right. Okay, so let's move on. Now, just like what we had before with arrays, when you make an assignment statement with a reference type, what you have is a copy of the reference and not a new object. Okay, so if you simply say, if A and B are two objects, then when you say A equals B, you're simply aliasing. Okay, so let me make that clear. So if A is some object and B is some object, each one has a memory address, and then if you go about saying A equals B, then A is basically pointing to what B was pointing to. Okay, so and then what happens as a result is this memory here is dangling because nothing is pointing to it, because A now simply points to whatever B was pointing to. Okay, but because of garbage collection, you end up getting this memory back. So in other words, the issue of aliasing also applies to reference types or objects. Okay, now we can pass objects as arguments to methods, and we can also use an object as a return value from a method. All right, and that is what is illustrated in this example here called flipsmax. And what this program does is it simulates capital T number of coin flips, and it finds out which one is the winner, if it was heads or the tails. Okay, so let's walk through this program. So here again, we import the counter data type and these two library of static methods. The program is called flipsmax, and here we have two methods. All right, we have this method max. It's a static method, and it returns an object of type counter. So that's what we are saying here, that a method can return an object, and that's what max is doing. It's returning an object of type counter. And then max takes two counter objects as arguments, x and y. And that's what we're saying here. You can also have methods take objects as arguments. Okay, and what does max do? Well, it compares the tally of x and y by making calls to the tally method on x and on y, and we use the conditional operator to figure out which tally was bigger, and depending on which tally was bigger, we return the corresponding counter object. So if x's tally is bigger than y's tally, we return the x object, the x counter object. Otherwise, we return the y counter object. Okay, so this is a static method that takes two counter objects as arguments, and it returns the counter object that has a higher tally. Okay, so that's max. Now let's look at the entry point method, the main method. So what are we doing here? We first get a command line argument, capital T, as a string, and we convert it using the static method parsend to a primitive integer, capital T. And then we go about creating two objects, heads and tails, of type counter, and then we perform capital T number of flips. So all this is similar to what we did in the flips program before. And if we have a heads, so if std_random.bernoulli with the argument 0.5 returns heads, we increment the heads object by 1. Otherwise, we return increment the tails object by 1. So once the for loop is done, we have performed capital T number of coin flips. And then what we do is we compare the tally of heads and tails. We make a call to the tally method on heads and a call to the tally method on tails. Compare the two tally. If they are the same, then we simply print out the message that it was a tie. Otherwise, what we do is we make a call to this max method, to the static max method, giving it the heads and tails object as arguments. And whatever max comes back with, remember that max is going to come back with a counter object. All right, so this max is going to be a counter object. Which one is it? Well, it depends on it depends on the tally of heads and tails. So if heads had a higher tally, max is going to return heads. Otherwise, max is going to return tails. But in either case, what is being returned is a counter object, and that is concatenated. So this guy here is counter object that is concatenated with a string. So what do you think happens here? Well, here again, this guy needs to be promoted to a string, and the way that happens is the toString method of the counter object that is returned here, let's call it O. So the toString method is invoked on that, and whatever that ends up being, that is what gets concatenated to the string here, and println simply prints that concatenated string. Okay, so this O is either going to be the heads object or it's going to be the tails object. Okay, so that's flips max. Let's look at some output. We first compile the program and then we run it by saying Java flips max, giving it an argument capital T equals 1,000,000, and the program comes back with this output saying that this on this run it was heads that won. Okay, and it had this for its tally. Okay, let's move on. Now, in Java, every value of any non-primitive type is an object. So if you have something that is not a primitive, we know that there are 8 primitives in Java. So if you have a value that is none of those types, then we know that it is an object. Okay, and in particular, arrays are objects. Okay, so keep that in mind. Now, inside of an array, the entries can be of any type. including reference types, i.e. they can be objects. So it's perfectly okay to have an array of objects. And we already have an example of this. The inside of the special entry point method, you have this as an argument to main, right? It's an array that stores the command line arguments. But what type of an array is args? Well, it's an array that stores objects of type string. Because string, remember, is not a primitive type, it's a reference type. So we already have an example of an array that stores objects. In this case, args is an array of string objects. Okay? Each of these strings being a command line argument. Okay, so let's look at another example where we illustrate this idea that arrays can contain objects. Okay, so this program is called roles, and what it does is it simulates capital T roles of a die, and it simply keeps a tally on how many times each of the sides appeared, right, as the face value of the die. Okay, so here again we import the ADT counter, and then we also import two libraries of static methods, stdout and stdrandom, and then we have the program definition. It's called roles, and roles simply has one method, the entry point method. Okay, main. So what are we doing here? We first get a command line argument, capital T as a string, which we convert into an integer before we assign to capital T. Okay. And then we initialize a variable called sides to 6 because we are simulating the role of a 6-sided die. And then what we do is we create an array called roles. Okay. Now roles is an array of objects of type counter. So roles is an array of counter objects. Now how many elements does roles have? Well, it has sides plus one number of elements. So sides was 6, so roles has 7 elements. And we created with a size of sides plus 1 and not sides because we're not going to like worry about the 0th element. Okay, so indexing becomes easier that way. So we're going to ignore the 0th element of the roles array. All right. Okay, now before we proceed, let's see what we have right after this line in memory. All right, so roles is basically an array all right, with 7 elements. Index 0, 1, 2, 3, 4, 5, and 6. We're not going to worry about this guy here. So once this line is done, since roles is an array of objects, all these guys are initialized to null. Okay, so to begin with, everything is null. Null, null, and so on, all the way here. So everything is a null. Okay, and then what we do in this for loop is we explicitly initialize this array to contain objects of type counter. Okay, so I goes from 1 all the way up to sides, which is 6, and we simply say the ith element in roles is a new counter object whose ID is I apostrophe S. Okay, so after the first iteration, this guy here is going to be a counter object whose ID is the string 1 apostrophe S, and so on. And this guy here is going to be a counter object whose ID is 6 apostrophe S. Okay. So once this for loop is done, every element in roles is a counter object. Okay, so now let's look at the next for loop. So this is where we simulate the capital T roles of a die. Right? So T goes from 0 all the way up to capital T in increments of 1, and we get a random number between 1 and 6. and we do that by making a call to the static method uniform from std_random, and this returns a number between 1 and 7. All right, but remember that the way uniform works is the left bound is inclusive, the right one is not inclusive. So the number that we will get out of a uniform is from the range 1 through 6 inclusive. Okay, and then what we do is we use that random number, which is a number between 1 and 6, as an index into the roles array. All right, so we say roles at result. So when you do that, what is that going to be? Well, that is going to be one of these counter objects. The counter object sitting at 1, or the counter object sitting at 2, and so on, or the counter object sitting at 6. Okay, and then on that counter object we invoke the instance method increment and increment the corresponding tally by 1. Okay, so for let's say for the sake of argument that in a particular role result turned out to be 3. So in that case, what you do is you say roles at 3. So you say roles at 3. So if result was 3, roles at 3 is the counter object that is sitting at this index. And we simply call the increment method on that object and bump up its counter by 1. Okay. All right. So you can see that once this for loop is done, all these counter objects take on some like different counts, right? And the counts that they maintain are basically that the number of times the corresponding index showed up as the face value of the die. All right, and if you add up all those counts, you ought to get capital T. Okay, because that's the number of times that you're rolling the die. Okay, and then what we do in the last for loop is we simply walk through this array. Right, so I goes from 1 all the way up to sides in increments of 1, and we simply print out roles at I. But what is roles at I? It is a counter object, and we print that counter object. And going back to what we said before, recall that when you print an object, you're simply invoking its toString method, and whatever that string is, that's what you end up printing. So you're basically printing the string representation of the counter object roles at I. Okay. So that's how the program works. Let's look at some output. So of course you first need to compile the program, and then you say Java roles to run it with a command line argument of 1,000,000. So capital T is 1,000,000, and the program comes back with these counts. All right. So this is basically the number of times the face value 1 showed up. This is the number of times the face value 2 showed up, and so on. And each of these lines is basically what you get by printing the corresponding counter object from the roles array. Okay, so this output is roles at 1, and this output here is roles at 6. Okay, and so on. So that's a program that makes this point that array entries can be objects. So let's move on. Now let's look at examples of abstract data types. So here I'm showing you some of the standard Java system types from the java.lang package. So there's a type called integer with a capital E, a capital I, that is a wrapper for the primitive integer. So it turns out that in Java, for each one of the 8 primitive types, you also have a wrapper reference type, right? And we'll talk about this in a later lecture. This is basically a way of it provides a way of going back and forth between primitives and between the primitive types and reference types. Okay, so integer with a capital I wraps primitive int, double with a capital T wraps the primitive double, and so on. Right, and then there is also the string data type, which represents a sequence of characters. So these are all examples of abstract data types sitting inside of the java.lang package, right? So they are the Java system types. There are other Java types which are ADTs. So here is color sitting inside of the package java.awt that represents colors, URL sitting inside of java.net representing a URL, file sitting inside of java.io representing a file on the file system, and so on. Here are some types from this package from the authors of our text for performing file I/O. Okay, so in is very different from stdin, and it represents a file input stream, whereas stdin represented the standard input stream, and that's a library of static methods. Out is a file output stream, very different from the standard output stream, which is represented by stdout. Okay, so stdout and stdin are libraries of static methods, whereas in and out are ADTs. Okay. More types inside of this package. Well, you have something called date to represent a date, a calendar day. You have something called transaction that represents a transaction, and we'll talk about this type later on. Okay. So these are again examples of abstract data types from this package from the authors of our text. Some more types in that same package. You also have types such as counter, which we talked about before, for keeping track of the number of operations. All right, and then there is a type called stopwatch that you could use to instrument a piece of code, meaning to figure out how long it took for that code to execute. Some more types, we'll talk about these in a future lecture. Linked bag and linked stack. These are abstract data types representing a bag data structure and a push down stack. There are data types, abstract data types representing graphs. We'll talk about this later as well. So graph represents an undirected graph, and digraph is an ADT that represents a directed graph. Okay. So these are all examples of abstract data types. And then there is a data type called UF, which is a data structure that you can use to solve what is called the dynamic connectivity problem that we will discuss in a bit. And then there is another data type called depth-first paths that you can use to perform a systematic search on a graph, right? A systematic way of enumerating the vertices of a graph. Okay, so now let's talk about a couple of data types in some detail. So let's first focus on the string data type. Now the string data type, it's an abstract data type representing an indexed sequence of character values. So it's basically a string of characters. And here is the API for the string data type. It's by no means exhaustive. There are many more methods than what is shown here, but this should give you some idea on what are some of the things that are available in that data type. So you can build an empty string using this constructor. Now you can also, a string is somewhat special in that you can also build a string simply by saying string s equals the string Bob. Okay, so here we are building an object of type string called s that contains the sequence of characters Bob or Bob. Okay. Now, what can you do once you have an object of type string? Well, you can get its length. And remember, these are all instance methods. So the way you invoke these methods is on an object. So for example, you could say s.length to get the length of a string. And in this case, it's going to be 3. Right? So it's going to be, 3. Okay. What are some of the other methods? You can figure out the character at a particular index I within the string by making a call to the char at instance method. You can you can take a string and you can split it into some tokens using this as the delimiter. For example, if S is the string A, comma B, comma C, then saying something like S dot split using the delimiter comma will give you an array whose first element is the string A, the second element is the string B, and the third element is the string C. Okay, so that's how split works. So these are just some of the methods that are available inside of the string data type. You can use this method to compare two strings for equality. So you can say, for example, S dot equals another string T, right? And this is going to return true or false based on how the two strings compare. Okay. Now let's look at an example, a little example where we make use of the string data type to solve an interesting problem. So here, this method, the static method called isPalindrome, tests if this argument S is a palindrome or not. Now recall that a palindrome is a string that reads the same forwards and backwards. Okay, so for example, the string Bob is a palindrome. Similarly, the string Madam is a palindrome, right? Whereas the string cat is not a palindrome. So these guys read the same forwards and backwards, whereas this one does not. So this method here recursively figures out if this string is a palindrome or not. So how do we do that? Well, here's the base case. If the length of S is 0, we simply return true, saying that it's a palindrome. So an empty string is a palindrome, right? And here we have made use of the length method that is shown here to figure out the length of the string, right? So that's an instance method called on an object of type string, right? So that's the base case. Otherwise, what we do is we compare the character at 0 in the string with the last character at S dot length minus 1. So here we are making calls to the instance method charat and length. Okay, so we simply compare the first character with the last character. So if those are the same, and if everything in between is a palindrome, so that's the recursive call. So everything in between, meaning the substring of S starting at 1 all the way up to the last but one character. So that is also a palindrome, and if the first character matches the last one, then the string S is a palindrome. Okay, so that's a very nice recursive approach to figuring out if a string is a palindrome or not. So what we're saying is, whenever you have something like Madam, for this to be a palindrome, these two guys have to match, and everything in between has to be a palindrome. So these guys should match, and this stuff has to be a palindrome. And that in itself will recurse. So that will check if these two guys match, and if the stuff in between is a palindrome. Okay, so that's how the recursion works. And notice that here, in this method, we have made use of a few of the methods from the string data type, such as length, charat, substring, and so on. Okay, so it's a nice little example where we make use of the string data type. All right. Now let's look at another example of an abstract data type in some detail. So let's say that you receive an input sequence of pairs of integers where each integer represents an object of some type. Okay, and actually, let's assume that you have n such objects labeled 0 through n minus 1. So for example, if n is 10, then the objects can be looked at as these dots, labeled 0 through 9, right? And then you get these pairs. So pairs PQ, and when you receive a pair such as this, what it means is P is connected to Q. So when you get a pair, you check if P and Q are connected or not, and if they are not connected, then you establish a connection between the two. Now, for P to be connected to Q, there need not be a direct connection. There could be a direct connection, or it could be indirect. Okay, so P is said to be connected to Q if there is a direct or an indirect connection from P to Q. All right. So the goal of the dynamic connectivity problem is to implement a data structure that lets you decide whether or not a new pair of objects is connected. And if they're not connected, it lets you connect the two. Okay, and this data structure ought to be able to do it in an efficient manner, meaning it ought to be able to figure out if two points P and Q are connected or not efficiently, and if they are not, it needs to be able to efficiently connect the two. Okay, and the union find data type, UF for short, provides exactly that data structure that lets you address this problem efficiently. All right. So let's, before we look at the API, let's actually look at this input sequence. So we first get 4 and 3. Notice that 4 and 3 are not connected. So what you do is you establish a connection between the two. Okay. And then comes the pair 3, 8. 3 and 8 are not connected, so you establish a link. Then comes 6 and 5. They are not connected, so you establish a link. Then comes 9, 4, not connected, so you establish a link. Then comes 2, 1, well, they are not connected, so you establish a link. Then comes the pair 8, 9. Now notice that you don't have a direct link from 8 to 9, but 8 and 9 are connected because there is a path between 8 and 9. You can get from one to the other. Okay, so we don't establish a link between 8 and 9 because they are connected, though not directly. That's fine. So that's why this 8, 9 shows up in gray, meaning we simply ignore this pair and look at the next pair. All right. So 5, 0, those are not connected, so we establish a link. Then comes 7, 2, those are not connected, so we establish a link. Then comes 6, 1, not connected, so we put a link. Then comes 1, 0. Okay, 1, 0, there is no direct link, but there is a path from 1 to 0, so I don't establish a link. That's why it's in gray. And then comes the pair 6, 7. There is no direct link, but there is a path between 6 and 7, so no need to establish a link. So that's why this pair is also in gray, and I'm done processing all the sequence. All right, so as you can see, we repeatedly ask this question for every pair. Are the endpoints connected or not? If not, connect them. So we want to be able to perform these two operations very quickly, and that's what the union find data type allows us to do. So here is the API for the union find data type. We can build a union find data structure specifying the number of sites, capital N, or number of points, these dots, and that simply initializes an empty union find data structure with N sites. And then we can check, figure out the component identifier of a given site, right? And a component identifier is basically a number between 0 and n-1, right? It basically tells me which island this site P belongs to. Now here at this level where there are no connections, every site is its own island. Okay, so if I ask for if I say find of 4, I'm going to get 4 back because 4 is its own island, right? Whereas here, once all the inputs have been processed, there are 2 islands now. Okay, so this is one component and this is one component. Okay, so for each site in this island, if I make a call to find, I'm going to get some number representing that island. And that number is going to be implementation specific, and we'll talk about that in a later lecture. And then similarly, if I ask for if I call find for any of the sites in this island, I'm going to get the same number. Okay, which is the component identifier for that particular island or component. Right? Okay. So find basically tells you which island or which component the site P belongs to, and it's simply a number between 0 and n-1. Count is a method, an instance method, that tells you the number of components. So once all the input pairs have been processed, you can use this method to figure out the number of islands that you're left with. In this particular example, count is going to return 2 because there are 2 components or islands. And then there is the connected method, which is a predicate that tells if the site P and Q are connected to each other, meaning whether or not they belong to the same island. So for example, if P and Q are 0 and 1, then connected is going to return, once all these input pairs have been processed, connected is going to return true because 0 and 1 belong to the same island. Whereas connected of 0 and 9 is going to return false because 0 and 9 belong to different islands, right? Okay, and then union is the method that you would use to actually establish a connection between 2 sites. So let's say that 2 sites P and Q are not connected. So in that case, you want to connect them, and the way you do that is by making a call to the union method from the UF data type. So that's the API for the union find data type. Let's now look at a simple client of the union find data type, meaning a program that makes use of the UF data type. So this program is called UF client. It imports this data type called weighted quick union UF, and this is simply one particular implementation of the UF data type from the previous slide. There are several implementations that exist. We'll talk about this later on when we get to the union find data structure in a future lecture. But this is just one of the several implementations, right? And then these are our usual libraries of static methods, stdin and stdout. Okay, so how does the UF client program work? Well, it has just the entry point method, the main method. We first read from standard input the number of sites. Okay, so the input for this program is standard input. We first read the number of sites, capital N, and then we initialize a union find data structure with n sites by making a call to the constructor of the union find data type. So that's what builds union find data type, or initializes it with n sites. Okay, and then what we do is we repeatedly receive pairs of numbers from standard input. So as long as stdin is not empty, we get a pair. So P is one number from stdin, Q is another integer from stdin, and then once we have P and Q, such as 4, 3 for example, we check if P and Q are connected or not using the connected instance method from the union find data type. Okay, so we say uf.connected PQ, and if they're already connected, what do? We simply continue with the next iteration. Okay, here's a very nice use of the continue statement. So if P and Q are connected, no need to establish a connection, simply continue with the next iteration, meaning look at the next pair. Otherwise, if you're here, it means that P and Q are not connected, in which case you make a call to the union method from the union find data type, and you establish a connection between the two. Okay, so that's what you do. And then you simply print out a message saying that you actually linked P and Q together. Okay, so, and once all the pairs are processed, the while loop is done, because standard in.isEmpty is going to return true, and this whole thing is false, so you're out of the while loop. And then you simply make a call to the count method from the union find data type and print the number of components or islands. Okay. Now, here what I'm showing you is a file called tinyuf.txt that simply stores these pairs of numbers. Okay, the very first number is the number of sites n, and then you just have these pairs of numbers. So 4, 3 is this pair, 3, 8 is this pair, 6, 5 is this pair, and so on, all the way up to 6, 7, which is this last pair. So this file is basically storing an input for this program. And I'm going to now run UF client by saying Java UF client, and I use the redirection operator to feed this input into the program. Okay? And the program simply processes all these pairs, and it prints out the pairs for which it actually established a connection. So 4, 3, 3, 8, 6, 5, and so on. Notice that it did not print 8, 9 because 8 and 9 were connected at that point. So you don't see that in the output. Similarly, you don't see 1, 0, and 6, 7. Right? And then once all the pairs are processed, it prints out the message saying that at the end there were 2 components. All right? So all the sites were sorted into 2 components. So this is one component, and that's one component. Okay, so within a component you can get from any site to the other, but you cannot get from a site in one component to a site in another component. Okay, so that's a very nice application of the union find data type. It's a nice little client. All right, so now let's talk about how you implement an abstract data type. So an ADT is implemented as a Java class, okay? And inside the Java class, you put all the code that forms the ADT. And this code includes instance variables or attribute names. It includes constructor definitions and also instance method definitions, all right? And the name of the file has the same name as the class, and it has a .java extension. Right? So for example, if you're defining a counter data type, the name of the data type itself is counter, and it typically sits inside of a file that's called counter.java. Now, instance variables are also called attributes, and they define the state of each object. Okay? And unlike local variables, each instance variable can have numerous values, one per object. Okay. For example, going back to the counter data type, it's going to have an instance variable that keeps track of the tally, and each object of the counter data type will have its own value for tally. All right. So that's what we mean when we say that each instance variable can have numerous values, one per object. Okay. Now, constructors have the same name as the class. So we talked about this before, and they don't have a return value, not even void. Okay. So that's what makes a method a constructor. It gives it that special status. Same name as the class and no return type, not even void. And the purpose of a constructor is typically to initialize instance variables. So that's where you initialize your instance variables. Now, instance methods are what define the behavior of each object. And each instance method has a return type or void, and it has a signature and a body. So that's how you define an instance method. Okay, so you specify the return type, the name of the instance method, which is part of its signature, and along with the arguments, the formal parameters, and then you have a body inside of curly brackets. So the syntax for defining an instance method is very much similar to that of a static method. The only difference is an instance method lacks the static keyword. Okay. Now, when a client invokes an instance method, the action is the same as that for a static method, and one main distinction is that instance variables can access and perform operations on instance variables. Okay, It's very critical. Now, within an instance method or a constructor, the keyword this is a reference to the current object. It is the object that is being manipulated, or the object whose method or constructor is being called. Okay, so for example, when you say something like heads dot tally, then the tally instance method is being called on the heads object. So it's heads that is the object that is being manipulated. All right. So in this case, inside of tally, this refers to heads. It's a pointer to heads. And then later on, let's say you say something like tails dot tally. So in this case, the object that is being manipulated is tails, and this keyword is a reference to the tails object. Okay. So this is simply a reference to the object that is being manipulated, or the object on which the instance method is being called. Okay. Now, the most common reason for using the this keyword is because fields or instance variables are shadowed by a method or constructor parameter. Okay, so let's say you have a method or a constructor whose parameter has the same name as the instance variable. Then how do you tell the difference between the two? Well, what you do in that case is you qualify the instance variable using the this keyword. All right. So if you have let's say if you have a field called x, or an instance variable called x, and if you also have, so this is a field or instance variable, and let's say you also have a local variable x. So how do you tell the difference between the two? Well, you would disambiguate by saying this dot x for the field and just x for the local variable. Okay, so that's how you can tell the compiler which one you're talking about. And the advantage of working with this keyword is that then you don't have to come up with different names for your parameters from the instance variables. You can continue using the same name and just use this keyword to differentiate between the two. Okay, so now let's talk about implementing the counter data type. Okay, so here is the API for the counter data type that we saw before. How would you implement this data type? So what are some of the instance variables that we will need? Well, it turns out that we will need two instance variables or attributes here. One to keep track of the ID of the counter, and another one to keep track of its tally. And so the ID is going to be of type string, and tally will be an integer. Okay. So here is the implementation of the counter data type. Right? Now this implementation sits inside of a file called counter.java, and it sits inside of this package. Okay, that's the package statement that you see there. And counter, remember, is a comparable data type. So that's why it has this additional syntax. It implements something called the comparable interface. We'll talk about this later on. And it's this syntax that makes counter comparable, meaning you can compare two objects of type counter for order, such as like which one is smaller than the other and so on. All right? But we'll talk about that later on. Okay, so here are the instance variables for the counter data type. You have the string ID. We have declared it to be final, which means that it can take on a value only in the constructor and nowhere else. So you can assign it a value only in the constructor and in no other place. Okay, and that's how the final keyword works. And then it's always a good idea to make the instance variables private, which is what we have done here. So the client, so this goes back to what we said in the first slide, that an ADT is something whose representation is hidden from the client. So the client does not know or see the instance variables. So this is also called data encapsulation, right? Okay, so ID is one of the instance variables, and then the other one is count, which simply keeps track of the tally, and it's a primitive int. And then the first thing that you see is the constructor definition. Of course, the order doesn't matter, but it's common practice or a good idea to have the instance variables first, and then the constructor definitions, and then the methods, and so on. Okay. So what we have next is the constructor definition. Notice it has the same name as the type. No return type, not even void. That's what makes it a constructor. And then the constructor here takes a single argument, the string ID. And what we do in here is simply take the value of this parameter and we assign it to the instance variable ID. Notice that ID, the parameter ID has the same name as the instance variable, so we have to disambiguate between the two using the this keyword. So on the left hand side we are talking about the instance variable ID, whereas on the right hand side we are talking about the parameter. Right? So this is what I mentioned in the previous slide. When a parameter shadows an instance variable, we need to use this to tell the difference between the instance variable and the parameter. Okay, so what we are doing here is we are simply assigning the value of the parameter to the instance variable. And once that is done, once the constructor is done, we have an object of type counter initialized, okay, with the given ID. And count, since it's a primitive int, when you declare it as such, it takes on the default value 0. But we could also be explicit here and initialize that as well, though it's not necessary. So you could say count equals 0 if you want to make the initialization explicit. And notice that here I didn't have to say this dot count because there is no parameter called count that is shadowing the instance variable, though it doesn't hurt to say this dot count. So it is perfectly okay to say this dot count equals 0. That's fine too. Okay. All right, so that's the constructor definition. What about increment? That's straightforward. You simply increment the current tally by 1. So you say count equals count plus 1 or count plus plus. Here again, I didn't have to say this dot count because there is nothing shadowing the instance variable count. But again, it doesn't hurt. You could say, so it's perfectly okay to say this dot count plus plus. So you can always use this keyword to refer to an instance variable or to an instance method, for example, for that matter. Okay, so that's how you would implement the increment instance method. What about the tally method? That's extremely straightforward. You simply return the current value of a count. So that's what we do. Okay, here again, it's perfectly okay to say return this dot count if you want, but we don't really need to do that. What about the toString method? So note that toString has been overridden here. All right, so we don't want the default implementation of toString that's given to us from object. Instead, we override it, and what we return is a call to tally, which simply returns the current count of this counter object, and that is concatenated with the ID, the string. Okay, and that's what we end up returning. So we simply, so for the string representation of a counter object, we return a string that contains the tally of the counter along with its ID. Okay, so this is how we get the string representation of a counter object. And finally, the compare-to method is what allows us to compare two counter objects. So it's an instance method. So we are basically comparing this counter, the counter object that is pointed to by this keyword, with that counter object. Okay, and if this counter's count is less than the other one, we return a negative number. If this counter's count is greater than the other guy's count, we return a positive number, +1. And when they're precisely the same, we return 0. That's how compare_to typically works. It returns a positive number if this object is larger than the other object by some measure, negative number if this object is smaller than the other one by some measure, and 0 precisely when they are the same. Okay, we'll talk about this in some detail later on, later in this lecture. So this method here, Comparator, is somewhat special. It's a method that sits inside of this thing called an interface. Okay, and that's what allows us to compare two objects, in this case two counter objects. Okay. All right, so that's how you would implement the counter data type. It's rather simple. Okay, so now let's talk about some data type design principles. Now, interface inheritance or subtyping is what we're going to discuss here, and that idea basically specifies the relationship between seemingly unrelated classes by providing in an interface a set of common methods that each of the implementing class must contain. Okay, so it's the interface that specifies any common functionality between these seemingly unrelated classes. So for example, you might have two abstract data types, one called counter to keep track of counts, and another one called, let's say, a student for representing the student in a university. So these are very different data types or classes. But we may want both of them to be comparable. For example, we want student objects to be comparable. Similarly, we want counter objects to be comparable. So what we do is we have these two guys, student and counter, implement an interface called comparable. Okay, or something like that. So it's that interface that provides a set of common methods. Okay. So the first set of interfaces that's going to be very useful for us is the comparison interfaces. Okay, and there are two of them. The first one is called comparable, that sits inside of the java.lang package, and the other one is called comparator, which sits inside of java.util package. Okay, so let's first focus on the comparable interface. Now, an interface is almost like a class with a fundamental difference in that an interface only lists methods and does not say anything or does not provide an implementation for those methods. All right. So comparable is an interface that just has one method in it, one method declaration, right? And that method declaration is the compare_to method. So compare_to, it's an instance method, and it takes as an argument an object O of some type T. Okay. And what is the purpose of this method? Well, it compares this object where this object is basically given by this keyword. It's the object on which the compare_to is invoked. Okay, so compare_to simply compares this object with O, right? And it either returns a positive number, negative number, or 0. The convention is that it's supposed to return a positive number when this object is bigger than O by some criterion. It's supposed to return a negative number when this object is smaller than O by some criterion, and precisely 0 when this is same as O. Okay, so that's how compare_to is supposed to work. Again, comparable only specifies this method as a declaration. All right, It does not say anything about how it's implemented. It's the job of the data type that implements this interface to provide that meaning, to provide that definition. All right? And going back to the counter data type, that's exactly what we did there. So the counter data type implemented comparable, and hence it had to provide a meaning for this method. And now you can go back and check that the way we implemented this method there sticks or abides by this convention. It returns a negative number when this counter is smaller than the other counter, a positive number when this counter is larger, and 0 precisely when the two counters are the same. Okay, so it's the counter data type that provided a definition for this method by implementing this interface. All right, so any type that implements this interface is the one that will give meaning to this method. Right? Okay, so that's one of the comparison interfaces. The other one is comparator that sits inside of java.util. Now, what's the need for this? Why shouldn't this suffice? Well, if you have a data type that implements this comparable interface, then it can compare two objects of that data type only by one criterion. And that's basically what you use to implement this compare to method. But what if your data type has several instance variables that you would like to use when you compare objects of your data type? All right. So for example, you might have a student data type that you want to be comparable, but the student data type might have several instance variables, for example, of a name, a GPA, and then and other things such as email, and so on, and so on, and so on. So what if you want two student objects to be comparable by each one of these instance variables? Well, if you want to do that, then comparable interface is not enough, because with this you can just use one of these instance variables or one particular combination of them to make the student data type comparable. But if you want alternate orderings, then you need something more. You need the comparator interface. Okay. So how does comparator work? Well, it is an interface, and it just has one method called compare, and that takes two arguments, O1 and O2 of type T. And just like compare to it returns an integer, and it returns a positive integer when O1 is bigger than O2. It's supposed to return a negative integer when O1 is smaller, and 0 precisely when the two are the same. Okay, and it's an instance method, and it so it's called on an object. Okay. Now, with the comparator interface, you can think about implementing alternate orderings. Okay, so for example, you can have the student data type implement comparable to provide an ordering by, let's say, name, and then you can define a whole bunch of comparators for each of the other instance variables. Okay, so you can use a combination of comparable and comparator to provide any number of orderings for your data type. Okay, and that's what I'm going to illustrate in the next example. So this data type is going to be called planet, and it's going to represent one of the planets or any of the planets in our solar system. Okay, and for us, each planet is going to be characterized just by two things: its name and its and the number of moons that it has. Okay, and that's and those are what make up the instance variables for the planet data type. All right, and our planet data type is going to be comparable, so it's going to implement the comparable interface. So this is Java syntax that says that two planets are comparable. Okay, so we do that by saying planet implements the comparable interface, and this is the interface that I talked about in the previous slide. All right. Okay. Now let's go through the implementation. So we have two instance variables, the name of the planet and the number of moons. Name is a string and moons is a primitive int. We have the constructor that takes the name of a planet and the number of moons, and it simply initializes the object. It assigns the name to the name and it assigns the moons to the moons instance variable. Notice that the parameters shadow the instance variables, so we make use of the this keyword to disambiguate. Okay, so that's the constructor. Then we have a getter method called name, which simply returns the name of the planet. So that's an instance method. We have the moons method that simply returns the number of moons. So that's another getter that returns the number of moons. And then comes the compare_to method. Now, whenever you have a type implement an interface, you have no choice but to implement all of the methods that are declared in that interface. Okay, so you have to do that, otherwise the compiler is going to report an error. Okay, but in this case, comparable, we know just has one method, the compare_to method. So we just need to implement that, and that's exactly what we have done here. Okay, so compare_to, which compares this planet and the planet O. So that's the other planet which is being compared to this planet, on which compare_to is called. Okay, and it returns an integer, negative, positive, or 0, depending on how the two planets compare. And here in this compare_to, it chose to compare two planets by their names. Okay, and that's what we're doing. And now remember that name is a string, and it turns out that in Java, strings is comparable. Okay, meaning string plays the same exercise, same game. It also implements the comparable interface. So the advantage then is that I can make a call to the compare_to method inside of string to compare two strings. So that's really nice. And that's exactly what I'm doing here. I'm comparing the name of this planet with the name of the other planet, o.name, using the compare_to method that sits inside of string, because strings are comparable. And what does this method return? Well, it goes by the convention. It returns a negative number if this string is lexicographically smaller than the other one. It returns a positive number if this string is lexicographically larger than the other string, and it returns 0 precisely when the two strings are the same. Okay, that's how compare_to is implemented inside of string. And we take advantage of that. So we simply return whatever compare_to in string returns. All right. Okay, so we have managed to make planet comparable by their names. But what if we want planets to also be comparable by the number of moons? So we'll talk about that as an alternate ordering in a bit. And before that, let's just look at the toString method, which is very straightforward. So the toString method, again, it's a method from the object data type that we override here. And the implementation that we provide is the name of the planet, comma, the number of moons. So that's going to be our string representation of a planet object. Okay. All right. And now comes the alternate ordering. All right. And this is how we also provide an ordering based on the number of moons. Okay. The way we do that is as an inner class that is static and also public, and this class is called moon order because it's going to provide an ordering on planets based on the number of moons. And that, notice, implements the comparator interface from the previous slide. All right. And since it implements that interface, it has no choice but to implement the corresponding methods in that interface. And there is just one method, which is compare, that takes two objects, in this case planet objects P1 and P2, and returns an integer. positive number, negative number, or 0. Okay, and the implementation is extremely elegant. It's just a one-liner. We simply get the number of moons of P1, number of moons of P2, and return the difference. Now, convince yourself that this is the right thing to do and that it follows the convention. What if P1 and P2 have the same number of moons? In that case, this difference is going to be 0, and that's exactly what we want to return. 0 when the two planets have the same number of moons. What if this is a positive number? It means that P1 has more moons than P2. In that case, the convention says that we need to return a positive number, so that works out correctly. And when this is negative, it means that P2 has more moons than P1, and we're supposed to return a negative number, so we do the right thing there as well. Okay, so it's a very elegant implementation. Of course, I mean, you could have also done this using an if statement, but that's just too verbose. Okay, and this is a much shorter, elegant way of implementing the same thing. Okay, so that's how we provide an alternate way of comparing two planets by the number of moons. Okay, as an inner class. Now, if the planet data type had other instance variables, then you could have had more inner classes for each one of those for more orderings. All right. So, as you can see, using this approach, using a combination of comparable and comparator, you can provide any number of orderings for your data type. All right. Okay. So now let's look at the test client that sits inside of the planet data type. So what are we doing there? So we first create an array called planets of planet objects, and we initialize it with the size of 8, right? For the 8 planets that we have in our solar system. And then we initialize the 0th object in planets to be a planet object with the name Mercury and 0 for the number of moons. The next planet object to be Venus with that as the ID and 0 for the number of moons, and so on. And then the last object in the array planets, we set it as a new planet object with the name Neptune and 14 for the number of moons. Okay, so that's how we set up the array planets. And then what we do is, in this for loop, we simply print all the planet objects out. So when we do this, all the planets are going to come out in the order in which they went in. All right, in the order in which they were initialized in the array. And then what we do is we make a call to the static method sort inside of the arrays data type from java.util package, and that simply sorts the planets. But now the question is, how is it sorting by? What is the criterion that sort uses to sort planets? Well, when sort is invoked without an argument, just with one argument, the array, in that case, sort expects planets to be comparable. Okay, and in our case, that's fine because planet was made comparable. We did implement the comparable interface, so this is perfectly okay. So each object here is comparable. So what sort will do then is, in order to put those objects in order, it will simply make a call to comparator. So as it's doing its sort, whenever it needs to compare two planet objects, let's say P and Q, it will simply say P dot compare to Q. Okay, and this method does exist because the objects that go inside of the planets array, they are objects of type planet. Planet is comparable. It implements the comparative method that we talked about at the previous slide. Okay, so that's how sort is going to work. And how did we implement comparative? We simply compared two planets by their names. So this sort is going to be a sort on planets by their names. Okay, And sort is a method that has a side effect. It doesn't return anything, but it does sort these objects. Okay. So what are we doing next? We're simply going through the array planets and printing out the planet objects again. But now you expect the planets to come out in sorted order by name, by the names of the planet. Okay. And then what we do next is we make a call again to arrays.sort, but now we call an overloaded version of sort. There's another version of sort that takes an array that you want to sort, and in addition also takes a comparator. Okay, so this guy here is a comparator. It's a comparator object. Let's call it C. So what are we doing here? So when you make a call to this particular version, then the first array need not be an array of comparable objects. Okay, it could just be an array of objects. But if you do that, then you need to tell sort how two things from this array are going to be compared. And the way we do that is by specifying a comparator object. Okay, and this is a comparator object because remember, moon order was a static class, public static class inside of planet. So you can refer to it as the type name dot the class name. And then when you put these parentheses around, what are we saying? We're simply calling the constructor of moon order, okay, along with this keyword new. So this whole thing is essentially an object of type moon order, which implements the comparator interface. So this object C is a comparator. Okay, so now when sort needs to compare two objects from P and let's say P and Q from planets, how is it going to do it? Well, it's going to make use of the comparator. Okay, so it's going to say the comparator object C dot compare, not compare to, compare, because that's the method from the comparator interface, and it's simply going to give it the two planet objects P and Q. And this, of course, is going to return a negative number, a positive number, or 0, depending on how P and Q compare. But how did we implement the compare method in moon order? Well, we compared the number of moons of the two planet objects. So now you know how sort is going to sort planets. It's going to sort them in ascending order of the number of moons. Okay, so now when you go through the array planets and print the planet objects out, you expect the output to be sorted by the number of moons. Okay, so that's how things work. So that's how you define a data type, a comparable data type, and you also support alternate orderings. All right, and these are the different ways in which you invoke arrays.sort. In the first case, just with your collection that you want to sort, but in that case the collection has to be a collection of comparable objects. And in the second case, it just has to be a collection of objects, but in that case you need to specify a comparator, which is what we're doing here, and the sort will simply make use of that comparator to put this collection in order. Okay, all right, so now let's look at some output. So we run this program by saying Java planet, and what we see here is exactly what we expect to see. In the first instance, when we printed all the planets, it just came out in the order in which the array was created. So this is basically ordered as initialized in the array. And in this case, the second time around, when we used arrays.sort to print the planets array, to sort the planets array, and then we printed the objects in the array, things are sorted by name. Okay, and then in this case, we made a call to arrays.sort by specifying planets as the first argument, and we gave the moon order comparator as the second argument. So here, and when we print planets out, they come out in sorted order of number of moons. Okay. All right. So I hope as this program illustrates nicely how you work with the two interfaces, comparable and comparator, to make a data type comparable, and also to support multiple or alternate orderings. Okay, so the next set of interfaces that's going to be very important for us is the iteration interfaces. All right, so here again, you have two interfaces that we need to look at. The first one is called iterable. All right, so let's say you want to make a data type iterable, meaning you want to iterate over its values. All right, so how do we do that in Java? Well, what we do is we have that data type that we want to be made iterable, implement the iterable interface. Now, iterable is an interface, meaning it only lists method declarations without saying anything about their definitions. And iterable simply has one method, which is called the iterator method, right? And so any data type that you want made iterable needs to implement this interface, meaning provide an implementation for this method. And what is this method supposed to do? Well, it's supposed to return an object of some iterator. And what does that mean? Well, that iterator needs to implement this interface called iterator sitting inside of the java.util package. Now, this is an interface with these three method declarations. So any any iterator type that implements this interface needs to provide an implementation for all these types, right? Now, for all these methods. Now, we are not going to provide an implementation for remove at all. So our iterators are not going to support the remove operation. So we will leave this implementation empty all the time, right? But we will provide implementations for these two methods. Okay, so to summarize, the way you make some data type iterable is that you have the data type implement the iterable interface, which means you need to provide an implementation of this method. And the way you implement this method is by returning an object of type iterator, and that type will implement this interface and provide implementations for these two methods. Okay, so we are not going to worry about remove. So we're going to look at an example of this in a bit, but before that, just keep in mind that if you have an iterable data type, iterable type, which includes arrays, then you can iterate over its values, or you can enumerate over its values using what is called the enhanced for statement, which is also called the for each statement. All right. So let me give you an example. So let's say you have an array of strings called DOW for days of the week, and it is initialized using this initializing declaration syntax for arrays as simply an array that contains all these 7 strings, Sunday through Saturday. Right. And as mentioned here, arrays are iterable, so I can use this enhanced for loop syntax instead of the traditional for to walk through the values of this array, and that's what I'm doing here. So the syntax is fairly straightforward. So you say for some type name colon the name of the iterable. So the name of the iterable is DOW, this guy here, and then we put a type. This is basically the type of each element in that iterable. So in this case, it's a string, and this is simply a name. Okay, and then what are we doing in the for loop? We are simply printing out that string. So how does this thing work at runtime? Well, in the first iteration, S is going to take on the first value in that iterable, which is Sunday, and that's what we print out. So the first output is going to be Sunday. And then in the next iteration, S is going to take on the value Monday, and we're going to print that. So the second output is Monday, and so on and so on. And in the end, S is going to take on the value Saturday. We print Saturday, and then the for loop is done because we have exhausted the iterable. Okay. Now, it's very instructive to understand what sort of code this internally translates to or is roughly equivalent to, because only then you will understand how this construct here, this enhanced for loop, sort of relates to these things that we discussed here, right, with iterable and iterator. Okay, so this enhanced for loop basically translates to this while loop here. So we have this string array again, days of the week, and then this for loop translates to this piece of code, right? So the first thing that we do is, out of the iterable, DOW, we get an iterator. So DOW.iterator, and that's basically a call to this method. So this method is an instance method that you call on something that is iterable. Well, DOW is iterable, so this is perfectly legal. Okay, so that gives me an iterator, which is an object of type iterator. Okay, but what is iterator? Iterator is something that implements this guy here, which means I have access to all these methods. So what is the while loop saying? The while loop is saying, as long as this object iter has something to iterate, so that's a call to has next. So that's going to return true if there is something to iterate in the iterable, and false otherwise. So if that is true, then I go into the body of the while loop and I get the next element in the iterable object by saying iter.next. That's a call to this method here. Okay, and I assign that to S, and I simply print S. Okay, so for this array here, in the very first iteration, iter.hasNext is going to be true because there are all these elements that are yet to be iterated. And so I go in and I get the next element. So it is Sunday that gets assigned to S and gets printed out. In the next iteration, iter.hasNext still returns true because there are all these guys to be iterated. So I say iter.next, I get Monday, which gets assigned to S and printed out, and so on and so on and so on. And in the last iteration, iter.hasNext is still true, and I get the next element, which is Saturday, and I assign that to S and print it out. And then iter.hasNext is going to return false because I've exhausted the iterable. Okay, and that's when you're outside of the while loop. So it's, as I said before, it's very instructive to understand how this enhanced for loop relates to this piece of code here and how it translates to a while loop, because only then you sort of see how these two things work in tandem for an iterable data type. Otherwise, it's not at all obvious how these things work. Okay, so please take some time to understand this mapping between the enhanced for loop and this piece of code here. Okay, so now let's take a concrete example of a data type that we're going to make iterable. All right. So this data type is called called Fibonacci, and it's going to be iterable in the sense that you can use it to iterate or enumerate over the first n Fibonacci numbers. Now recall that the first 10 Fibonacci numbers are I'm sorry. So the 0th Fibonacci number is 1, the first Fibonacci number is 1, the second Fibonacci number is 2, the third Fibonacci number is 3, the fourth is 5, the fifth is 8, and so on and so on and so on. So how do you get the nth Fibonacci number? The nth Fibonacci number is simply the sum of the previous two Fibonacci numbers. Okay. All right. So how do we make this type iterable? So we define a type called Fibonacci, and it implements the iterable interface. All right. Okay, and since it implements iterable, we have no choice but to implement the one method that sits inside of iterable, which is this method here, iterator. All right, and we'll come to that in a bit. So for instance variable in Fibonacci, we just have n as a primitive end. So an n is going to denote the number of Fibonacci numbers that we want. All right. So if n is 10, we are saying we want to iterate over the first first 10 Fibonacci numbers, right? Okay, so in the constructor, what do we do? So in the constructor, we simply get the argument n and we assign it to the instance variable n. So that's this dot n equals n, okay? And now we have an implementation for the iterator method, which sits inside of the iterable interface. And what is that supposed to do? It is supposed to return an object of type something that implements the iterator interface, right? And that's exactly what we do. We return an object of type Fibonacci iterator. And what is Fibonacci iterator? Well, it's sitting right here as a private class. Okay, Fibonacci iterator implements the iterator interface. All right, what does that mean? It means that Fibonacci iterator needs to implement every method that is declared inside of this iterator interface. What are those methods? Well, it's hasNext, it's next, and remove. And as I said before, we are not going to provide any implementation for remove. We just leave it empty. But you still have to have it in there, because that's what it takes when, to implement an interface. You have to provide a body which could be empty for every method that is declared inside of an interface, right? So remove is always going to be empty for us. Okay, let's talk about the rest of the code. All right, so we have three instance variables here. The first one is count, and count is basically going to keep track of the number of Fibonacci numbers that you have returned so far, and initially it is set to 0. And then these two variables of type long, a equals 1 and b equals 1, are simply to keep track of the Fibonacci numbers in the sequence, right? And okay, and a and b are what we need to actually calculate the next number in the sequence. Okay. All right, now with hasNext has a very simple implementation. All that we need to do is compare count, meaning the number of Fibonacci numbers you have enumerated so far, against the total number that you need, the desired count, which is n. That's this guy here. Notice that an inner class has access to the instance variables of its outer class. Okay, so n is not defined inside of Fibonacci iterator, but Fibonacci iterator being private inside of Fibonacci has access to Fibonacci's private members. Okay, so this n is this guy here. So we simply compare count with n. If it is strictly less than n, then we know that there is something more to be iterated, so we return true. And when count is precisely n, we say that we have exhausted the iterable and return false. Okay, so that's straightforward. What about next? So next is supposed to return the next Fibonacci number. All right. So here, since we are asking for the next number, we increment count by 1. So initially count was 0. We now set it to 1. And then if count is less than or equal to 2, we simply return 1. Because the first two Fibonacci numbers are 1 and 1, we do it this way. Okay. So if count is less than or equal to 2, we simply return 1. But if that's not the case, then what we do is we calculate the next Fibonacci number as the sum of the previous two Fibonacci numbers. So a and b store the previous two Fibonacci numbers. We calculate the next one as the sum of a and b. And then we update a and b accordingly. Okay, so the way we do that is by saying we remember the current value for b in temp, and then we say the new value for b is the sum of the previous two Fibonacci numbers, a and b, and then we say that the new a is whatever b was. Okay, so that's in temp now, so you assign that to a, and then we simply return b. So initially, so this was a, sorry, so this A and B were 1. Okay, so we remember B in temp, and then we say new B is A plus B, which is 2, so this is now B. And then the new A is whatever temp was. Well, temp was 1, so this is now A. So A and B are like a sliding window, okay? And that's what you use to calculate the next Fibonacci number. Okay, so next correctly returns the next Fibonacci number. So that's basically how we make an iterable data type. All right. So now let's look at a test client. So we have this main method that receives a command line argument n. Okay. And then what we do is we use the enhanced for loop to build an object of type Fibonacci with n as an argument. Now Fibonacci is iterable, so this object is an iterable object, and hence a perfectly reasonable thing to put in here in the enhanced for loop. And then what are we doing here? We're simply iterating over this iterable. So in each iteration, I is going to represent is going to store the next Fibonacci number. Okay, and we simply print the ith Fibonacci number. Right, and here again, you should think about how this enhanced for loop can be translated into a while loop using what we discussed in the previous slide. Right? And that's a good exercise to follow. Okay, so let's look at some output. So when we run Fibonacci with the argument n, 10, meaning n equals 10, then it correctly comes out with the first 10 Fibonacci numbers. Okay. So that's how you make something iterable using the two interfaces, iterable and iterator. So the next thing to talk about is implementation inheritance, which is also called subclassing, and this is quite different from subtyping. All right, and subclassing is what allows programmers to define a new class as a subclass or a derived class that inherits instance methods and variables from another class, which is called the base class or the superclass. Now, you can explicitly have one data type inherit from another one, but that's not something that we're going to talk about in this class. All right, but in Java, every data type that you define implicitly inherits from the object data type, and we talked about this before. Okay, so even if you don't explicitly inherit from something, it still implicitly inherits from object. Meaning every data type that you define implicitly inherits everything from the object data type, right? Meaning the methods and so on. And some of the methods we already know. A toString method from object is inherited by every method, every data type that you implement, all right? Because toString is defined an object, and every data type implicitly inherits from object, so it inherits toString. Some of the other methods, as we discussed before, are equals and hash code and so on. Now, as mentioned earlier, Java provides wrapper types or reference types for every single primitive type. There are 8 primitive types in Java, and each one has a reference type. Okay, so Boolean with a capital B is a wrapper for primitive Boolean, integer with a capital I is a wrapper for int, and so on and so on and so on. Now Java automatically converts primitive types to wrapper types, and that's called auto boxing, and it converts wrapper types to primitive types, and that's called auto unboxing. So for example, when you say something like integer with a capital I x equals 42, notice that on the right hand side you have a primitive int, but Java automatically turns it into an object integer x, right? So this is what we call auto boxing. And then later on, if you say int y, primitive int y equals x, this object, what do we have? On the right hand side, we have an integer object. On the left hand side, we have a primitive int. Java automatically makes this conversion from object to primitive, and that's what we call auto unboxing. Okay. And we'll have something to say about this later on in a future lecture. Now, we know from our earlier discussion that object names are basically memory addresses. So if A and B are reference types or two objects, then saying A equals B simply compares their memory addresses, and that's usually not what you want. So if you are comparing two objects, you should always make use of the equals method and say A dot equals B, and never say A equals B. This is wrong for if A and B are objects, okay? Because whenever you do something like A equals B, you're basically comparing their memory addresses, and that's not typically what you want. Now, the ability to assign a new value to a reference variable can lead to orphaned objects, and this is something that we're already aware of. So let's say we create A as a data object and B as another data object, and then later on, if you go about saying B equals A, then B is no longer pointing to this guy here. Instead, B is pointing to what A was pointing to. And as a result, there is nothing pointing to this chunk of memory, and that is orphaned. So this thing inside of the box is orphaned in memory. But fortunately for us, Java supports garbage collection, so that memory is eventually going to be reclaimed and returned to you, right? But this is something that you should be aware of, this aliasing issue that can lead to orphaned objects. A few odds and ends. Now, immutable data type, for example, the date data type, has the property that the value of an object never changes once constructed. All right. So the only place where you assign values to instance variables is the constructor and nowhere else. And such a data type is called an immutable data type. Now, Java enforces immutability via the final modifier or the final keyword. All right. So if you say something is final, then that instance variable can take on a value only in the constructor and nowhere else. And we already saw an example of this. The string, the ID instance variable in Counter, we had made it final, and we assigned it a value only in the constructor. Okay. And if every instance variable is final, then your data type is immutable, right? Meaning you can assign values to those variables only in the constructor and nowhere else. Now, exceptions and errors are disruptive events that occur when a program is running. Now, Java system throws all sorts of exceptions, such as stack overflow error, arithmetic expression, array index out of bound exception when you access an array out of bounds, out of memory error, null pointer exception, and so on. So for example, if you say x dot some method name, or even to be more precise, if you say something like heads dot tally, so tally is an instance method in the Counter data type. If I call it on heads, and if heads happens to be null, then Java raises a null pointer exception. Okay, so you're not allowed to call a method on an object that is null. And we can also raise exceptions within a program. Okay, and the simplest such exception is the runtime exception that terminates the execution of a program and prints an error message. And this is the syntax for raising an exception. You use the keyword throw followed by the keyword new, and then you simply invoke the constructor of the exception data type, giving it any error message. Okay, so what we're doing here is really we're throwing an exception object, because this is nothing but is the syntax for creating an object, right? So what we are doing is we are throwing an exception object. Okay. And finally, an assertion is a Boolean expression that we affirm is true at the point in the at some point in the program. And if the expression is false, then the program terminates and reports an error message. So for example, if you say something like assert index greater than or equal to 0, so this is an assertion statement somewhere in your code, and if at runtime index, if it is greater than or equal to 0, this expression is true, which means that the assertion is successful and you just carry on with the rest of the code. But what if index is negative? What if it is less than 0? In that case, this Boolean expression is false, so there is an assertion error and the program immediately terminates, okay, with an assertion error message. Now here is an alternate syntax where you can provide a custom error message. Okay, so in this case, when index is less than 0, then the program terminates, but with this custom message. Okay. So assertions are quite useful, and we'll see some examples of this later on. Okay, so that's the end of this lecture, and it's also the end of our quick introduction to the Java programming language. So thanks for listening.